Oh, I forgot my chair, just a minute. Okay. Well, yeah, as I was just saying, so going straight on. First, we normalize the Ansatz trial solution. The trial solution was just this, the exponential, e to the minus alpha x squared. Your alpha here now is your parameter. That's the adjustable parameter. The parameter that we will vary, hence the label of the technique, the variational method. Okay. Alright, so let's normalize the thing first. So that will just be integral ut star ut by dx. Well, this ansatz here is a real function. So conjugating it, starring it, has no effect. So you're effectively just squaring it. Okay, so here's where the 2 comes from. And you integrate this, and you get, where does this come from? Well, it's in the table of useful integrals in the textbook, which is chapter E. I've shown you this several times before. Okay, chapter E, useful integrals, and there is I think the second integral in the list gives you, well, you can the equivalent of this, right? So okay, so squaring and integrating gives you this. That means you can calculate the normalization factor, which is 2 alpha over pi to the 4th. Okay, so if you square this and integrate it, this with this normalization constant, now you get 1. Okay, so it's been normalized. So we now have the ansatz, the trial function, normalized. It's here. All right. Now we're ready to calculate the expectation value for the Hamiltonian. In other words, the average measured energy values. Okay, so we want to calculate this. We will get a result that depends on the parameter alpha that we can vary. So as we vary alpha, we will vary the value of this. Right? Variational method. Okay, so plug it in. Now ut is this. We've got it here and here. So this will get squared, so you get 2 alpha over pi to the half. Okay, because I've got this squared, so times 2, so 2 over 4, a half. So this appears here and here. Now, the Hamiltonian operator, in this context, we're talking about a simple harmonic oscillator, SHO. So we know the terms in the Hamiltonian for the simple harmonic oscillator in quantum mechanical terms. So this is the kinetic energy terms, right? Sort of like p squared, the momentum squared over the 2m. That's the kinetic energy. So this is the quantum mechanical equivalent of the kinetic energy for the Hamiltonian, and this is the potential energy for simple harmonic oscillator. It comes from Hooke's law. The force when you stretch a spring, the returning force is like you have to pull it with the force outwards to stretch your spring, and the countervailing force pulling on your hand will be proportional to the extension of the spring, by how much you've stretched the spring. Okay, call that x, that extension, the stretched distance. Call that x. And the returning force will be proportional to that distance. That's Hooke's law. So the potential ends up, so the K here, sort of the equivalent of the, if you're talking about a spring, the stiffness of the spring. Anyway, so this is the potential energy, the kinetic energy, quantum mechanically. We know, you have these two operators. So this is your Hamiltonian for the simple harmonic oscillator. I ask you for homework to calculate all this, right? You'll need the table of useful integrals in the textbook, but you can do it. Ask you to do it for homework, and you'll end up with this. Okay. Now, as expected, given this is a parameter that we can vary, the variational method, we'll end up with an expression, formula, that depends on alpha. Right? That's not surprising. You've got all these alphas here in the exponential, okay? And it ends up being that. So do that for homework. Okay, prove it. Okay, so we now have a formula for the expectation value of the Hamiltonian, and we will now differentiate this expectation of a hat, this with respect to alpha, so that this is minimized, takes a minimum value. We'll choose an alpha so that this term here, which is this, is minimized. Right? It's just a high school maxima and minima theory calculus that you did in, I don't know, when you were, 18? Something like that. I'm guessing. Most countries do calculus at high school nowadays, I guess. Alright? So you can calculate the value of alpha when this gets minimized, when this is minimized, and it works out to be n omega over 2h bar. Okay, do that for homework. Do all this. By actually doing it, you get hands-on experience. You get the experience of calculating it, and so it sticks in your memory better, right? So useful didactic technique, adjective of what does didactic mean? Useful for educative purposes, something like that. Okay. All right. So you differentiate this. In other words, this with respect to alpha, the gradient to be 0. If it's the gradient at the minimum point, the gradient will be 0. You solve for alpha, you get this, and then you can plug this alpha into here, which will give you the expectation for h, and that will be your estimate of your E0, your ground state energy, your lowest energy. Right? So we know, by doing this, we've got alpha as this value, and then we can plug that alpha into the ansatz, which is here, right? Now it's normalized, so that, well, we know what alpha is now, so for alpha here we can plug in this, and that's done. Now you've got a 2 above and a 2 below, so they cancel. So what are you left with? M omega over pi h, M omega pi h, right, to the fourth, okay? To the quarter, sorry, okay? So there's your normalization constant by plugging in the alpha. And the alpha here, well, you just put this in, so m omega over 2h bar x squared, there it is. Okay, there's your estimated, approximated eigenfunction. That it's your trial function that you varied by doing this, differentiating with respect to alpha, and you got this. Now, actually, this value here is the actual value from simple harmonic oscillator theory. So the approximation is perfect in this particular case. Usually that's not the case. It's special. All right. Now, so we have the trial function now. Normalize this. So that's your function. Now, what's the corresponding for this? What's the corresponding eigenenergy, the ground state energy with this ansatz? Now, how do we get that? Let's see. Where will that come from? Well, the expectation value for the energy is this, right? This. So just plug in alpha that we found, which was this. Plug in that value of alpha to here and here. Do this for homework, okay? And you will get this. A half h bar omega. Aha! Now you know from simple harmonic oscillator, SHO quantum mechanics theory, you know that is the correct lowest eigenenergy. Right? So yeah, it all fits. Not surprising. Okay. Now, so we've solved our first example of using the variational method. Now, to give you a little bit of contrast, now you can't get better than perfect, right? So let's try a different eigenfunction and see if we get something a little bit worse. So you know, expect that, right? Just common sense. It's going to be worse. You can't get better than perfect. You know, zero error. Anything else, you'll get some error, right? So let's try this ansatz. And again, you may ask, well, where the hell did that come from? Again, just fell out of the sky. Well, it's one of the reasons why it's used here in the textbook, again for didactic reasons. When you come to integrate this, you know this kind of stuff, when you're integrating it, this particular form is easy to integrate. So it's a bit like, maybe you've heard of that joke. It's late in the evening. Let's say it's a century ago. You're in London with what I call pea soupers, pea soup. In other words, the pollution in London, before people became really conscious of how dangerous that is for cancer and lung cancer and all that stuff. Yeah, they just didn't know then. So everyone was burning coal like crazy for heat, and in the winters the air pollution was just horrible. It was just terrible. So you had the air was so thick when you had inversion layers that it was described as, you know, the air was as thick as pea soup, you know, which is opaque. You can't see through. You cannot see through pea soup. Okay, so pea soupers they were called. And so you come across some guy obviously looking for something on the ground, and so you decide to help him. So what did you lose? And he says, oh, my key, the key to my room. And oh, that's serious. Well, where do you think you lost it? And the guy says, I think over there. And then, well, that seems counter common sense. Why on earth is he looking here when he thinks that most likely he dropped it over there, somewhere else? So you ask him this, and he says, well, the light is better here, because there was a street lamp, a gas, an old-fashioned, century ago, gas street lamp, and actually. That sounds dumb, but it's not so dumb if you think about it, because if the probability